All right, so this is the general outline of Sn2. So now let's talk about the mechanism by which this goes. We've already seen some Sn2 type of chemistry with when the alkyne adds to a alkyl halide and then makes a substituted alkyne. That is an Sn2 mechanism. So to jog your memory, it's where you take a nucleophile. So yeah, I'll keep it general for this first example. You take a nucleophile and then I'll make a specific electrophile like this alkyl halide that has a chlorine here. The nucleophile, one of the lone pairs on it that makes the negative charge, will attack at this carbon. This carbon is electrophilic because there's a dipole here between the chlorine and the bromine. So that means the carbon has a partial positive and the chlorine has a partial negative, right? So you're creating this bond here, and then you cleave this bond onto the leaving group, which in this case is the chlorine. And you get this type of mechanism. And this happens in one step. So in that sense, we call this concerted. Which means that it occurs in one step, but to be more specific, it means that bonds break and form simultaneously. Which makes sense, right, when we look at the mechanism. Because in essence, we're showing that we're forming this bond between this carbon and whatever our nucleophile is. At the same time, we're breaking the bond between the same carbon and the leaving group, which is a chlorine in my somewhat general, somewhat specific example. So the takeaway here is that the bonds break and form simultaneously, which in part explains why there is two molecules that are required to determine the rate of the reaction. So any questions on this? We're very general at this point. I'll get slightly more specific with the mechanism here when I erase. All right, not seeing any questions. Hopefully I gave you long enough to copy this down if you wanted it. All right, so the next thing, so now let's talk about the transition state that is involved here. So we've shown the mechanism. And now the transition state. So first of all, transition state in general is a transient molecule that in which bonds are breaking or forming. You could have multiple bonds breaking and forming at the same time, like we do in an Sn2 type of mechanism, or you could just have one bond breaking or forming at a time like we do in Sn1. So we'll see the comparisons there. But transition state is transient, meaning it's not a stable species and it will immediately degrade into something more stable. So usually these are going to involve things like a carbon having a fifth bond or a carbon breaking a bond to end up having three bonds, things like this. Depends on the context. But ultimately, you're not going to have what you would consider a stable molecule with everything having its octet and all the stuff like that. So let's look at our mechanism once more. So now let me give a specific one now. So let's say we have this methoxide, this methyl group with a O minus is called methoxide. We'll learn about the naming convention for that when we get to the alcohol chapter. But so you don't need to worry about that, but just so you know. And then we need a leaving group or electrophile. So again, mechanism involves the oxygen coming in here, kicking out the chlorine, and then giving us now this guy, this ether, where this CH3 is this CH3. All right. Now, the transition state for this is in which you have a center carbon and your methyl group, that's this one, all right? And then your hydrogens that are on the carbon that you're attacking, and then your leaving group. And you need your leaving group and the nucleophile to be across from each other like I've shown here. And this should be a dotted line. Okay, the dotted line, the reason I corrected this is the dotted line represents that the bonds are breaking or forming. In this case, we're forming the bond between this oxygen and the carbon at the same time that we're breaking the bond between the same carbon and the chlorine, which is the leaving group. So this explains, or at least this visualizes when we say that bonds are breaking and forming simultaneously in the sense that this is concerted. It means that you're going to get a transition state like this. And notice if you considered the dotted lines as a real bond, the carbon would have 5 bonds, which as we know isn't really possible or stable. So this isn't really a species that you can isolate, but it exists, and we know it exists because it explains the mechanism by which the product is formed. So this shows a couple things. One, it's that the nucleophile has to attack from the backside relative to the leaving group, in the sense that this is a straight line. So this angle here between these two bonds that are breaking and forming is 180 degrees. That suggests that's what we mean by backside attack. So what that will do, if this is a chiral center, is it's going to invert the stereochemistry. So this means that you'll get inversion of stereochemistry. So what this implies in a practical sense is that you'll have to remember how to quickly identify absolute configuration of any molecule. So if that's something that's still a little bit hazy for you, definitely check that out. I have a couple videos on my channel that explain that pretty well. So if that's still confusing for you, just definitely take a look at that, because for these types of questions, you're absolutely going to have to be able to look at a product or a reactant or a product and know that it's R or S very quickly, because it's not even going to be directly involved in the question. It's just going to be, you're going to get an answer that will either have an R or S, and you're going to have to know based on this inversion which one is correct if it's an Sn2 mechanism. So let's apply this idea to just one more example. So let's say we have this electrophile now, and we're reacting it with the same nucleophile. You're going to see something like this often, where this is ionic. Don't worry about the solvent right now. We'll talk about, this is acetone. We'll talk about solvent effects towards the end. But when you see a ionic species like this that has a sodium metal and then in this case the oxygen negatively charged species, this is going to essentially supply the nucleophile, because we know that you can't just have a charged species just like in a bottle and it'll just be stable. Atoms want to be neutral. So if you just had this around in a bottle, it would protonate into the alcohol very, very quickly. So what we do to avoid that is react it with a metal, and this makes a salt. This is sodium methoxide salt that you can easily dissolve in something like acetone. And then now in the solution, you're going to have sodium metal ions and the methoxide ions. And then the methoxide ions are the ones that are going to react with this. So in essence, that's a long way of saying you can essentially ignore the sodium, because all it's doing is supplying your nucleophile in this case. So enough about that. Our mechanism would involve the negative charge on the oxygen attacking this carbon that's bound to the leaving group. This would cleave, and then you would get inversion of stereochemistry. So this one is, oops, not chlorine. It's the nucleophile that adds. And then we have table salt, sodium chloride, as a byproduct here. So this is one of the reasons why chlorine is often used as a leaving group, is because the byproduct is completely non-hazardous. So it's not something that you really need to worry about. And it's easy to isolate salts because they have different solubility in water comparatively to the organic material. So what we see here now is inversion of stereochemistry, since we've changed this from a wedge to a dash. But we can also confirm this by checking our absolute configuration. So this is 1, this is 2, this is 3. That looks like R. The hydrogen's in the back, so it is R. If we look at this one, here's our oxygen, that's our highest priority. The ethyl group is 2, methyl group is 3. This looks like R. The hydrogen's in the front, so this is S. And that is in fact an inversion of configuration. Now, you may say, well, this is obvious, right? We just went from a wedge to a dash, and you're right. In cases like this, it may be obvious, but they could draw it misleading just because they want you to determine the absolute configuration for yourself for that one. So like, for instance, well, I'll pause if there are any questions because I'll erase and show a different example, but I'm out of space. All right, no questions. So let's say now, instead, you have this. You will absolutely have to check if this shows an inversion of stereochemistry, right? So you have 1, 2, 3. That looks like S. It is S. And then you have 1, 2, 3. That looks like S. It is S. So since this is Sn2, if this was a multiple choice question and they gave you this as an answer, you know, let's say this is choice A, this is wrong because you've retained stereochemistry and you won't in a Sn2 type mechanism. Sorry, I lost my train of thought, but Sn2 type mechanism, you're going to have an inversion, not retention. So the correct answer would have the hydrogen off of that wedge like this. So if this is B, then this is what you want. So they look very similar. So you have to have a keen eye for this type of stuff to determine the right product. Okay. Again, I'll pause if there are any questions, but now I'm going to relate this to an energy diagram to explain why the transition state is more relevant to the rates determining stuff. Okay. Not seeing any questions, so move on. So now let's consider an energy diagram. So if you recall from general chemistry, you have energy on the Y axis and then time or reaction coordinate on the X. This is just the reaction is progressing as time is passing. So you'll have some, this is specifically for Sn2, by the way. You'll have your reactants at some energy level that is relatively stable. So let's call this specific leaving a specific situation. So we have like this and our sodium methoxide. And these are both on this line, but I just don't want to make this graph extremely long. So they're both on this energy level here. Then this will increase until you get to the transition state. In the transition state, kind of out of room to draw that well. Okay, the transition state, if we recall, is the one where the oxygen is forming to this guy, and then we have our hydrogens in and out of the plane like this, and then here's our methyl. All right, so here's our transition state at the peak of this hill, and then it'll crash all the way down because we know this is extremely unstable, so it'll crash down to the more stable products, which in this case is this plus the chlorine leaving group. All right, so a couple things about this is here we have activation energy. This is the energy required to get to the transition state. And then also here you have the enthalpy change between the reactants and the products. So in this case, this is exothermic because delta H is less than 0, right? You're going down in energy, so you have to release energy in order to get to the final product. So there's no intermediates in this reaction in an Sn2 mechanism because the bonds are forming and breaking simultaneously. We'll see in Sn1 that you form many intermediates because of the stepwise nature in which bonds break in specific orders, and then you can detect the intermediates directly. So, questions about this? So this, in essence, this is explaining that you need both of these species to make the transition state, and that is what's going to determine the rate. So because of this, now we know our rate is then a rate constant. There's always going to be some rate constant. You don't need to have them memorized, but times the concentration of the nucleophile times the concentration of the alkyl halide, which I'll represent as Rx. And like I mentioned before, the X doesn't have to be a halide. It just is in this case. It could be a different leaving group. Like we'll talk about tosylates and other stuff later, but they effectively work the same as a halide leaving group. So you just have to be able to recognize that it is a good leaving group. Okay. So questions on anything? So this is showing the thermodynamics. You'll hear these terms thrown out in class. You may have already heard them. The thermodynamics is this energy diagram. And then from the thermodynamics, we can determine the kinetics, which is the rate of reaction. So what you see here is both thermodynamics and kinetics, but they're related. All right, questions? Okay, so the next thing we'll talk about is leaving group ability. And this is another thing that students, in my opinion, mistakenly just put on note cards and memorize. You really don't need to do that if you understand the themes that govern the trends. Then if you know the trends, then you don't need to, you memorize less, just memorize the trend and then apply it. So in this case, the trend for leaving groups is the weaker base is a better leaving group. And you might say, well, so what? Now you just have to memorize what's a good and weak base, or what's a strong and weak base to do this. So like, how is that saving you from memorizing anything? Well, you'd be right if there wasn't this rule that we already talked about when we were talking about conjugate acids and bases. So we know that there's this relationship between a conjugate base and its acid. And it is that if there's a strong acid, then its conjugate base is weaker. So a strong acid equals a weaker conjugate base. So in essence, all you have to memorize is this first line, and then what is a strong acid, and then those two things you can apply to any leaving group. So now let's consider the series, the halide acid series, and which one of these is the strongest acid? Well, we know based on atomic size that the HI bond is the weakest bond, since iodine is huge and hydrogen is very small. There isn't a very good overlap between hydrogen and iodine. So this bond is weak, which means that it can easily dissociate and function as an acid. So this is the best acid based on atomic size. And then bromine is slightly smaller than iodine. So it's a worse acid, but it's also better than chlorine because chlorine is smaller still than bromine, and so on. So this is the trend for acid strength. So I'll just say acid here. So this is the strongest acid. So then its conjugate base strength is the reverse. So I minus is a weaker base than Br minus, which is weaker still than chlorine, which is weaker still than fluorine, because this is directly or indirectly proportional to the strength here. So if this is really strong, this is very weak. And again, this is now a weaker acid, so stronger conjugate base, weaker acid still, stronger conjugate base, weaker acid still, stronger conjugate base. So now relating this, you can relate directly to leaving group ability. So this is the weakest base, so this is the best leaving group. And then so on down the line. So the best leaving group of the halides is iodine by a lot. So much so that if you had a alkyl halide with an iodine and a bromine, your nucleophile is going to attack at 98% specificity to where the iodine leaves, not the bromine. So this explains why, without just having to memorize this list, if you know these trends, then you can apply it to different stuff. Because at the end of the day, we're going to expand from halides. All we're talking about so far is halides, but you're going to see other leaving groups, and you'll have to be able to rank their ability and fit that into this trend of weaker bases and their conjugate acids and all the stuff that we just went through. All right. So I think that is everything I wanted to talk about for Sn2. Feel free to ask any questions as I look at my note here. Oh, there's one thing I forgot that's important. Okay, not seeing any questions. So I did forget something very important, and it's the identity of the electrophile matters a lot, just like the rest of the stuff that we talked about. And the rule is that the less substituted electrophilic carbon is better for less substituted electrophilic carbon is better for Sn2. So what that says is primary or secondary alkyl halides are good, not tertiary. Tertiary won't work. And let's look at why. It has to do with the transition state. So I'll just go through this quickly since we've already seen this now a few times. But here the nucleophile needs to come in at this position, which causes this transition state. Right. So if these hydrogens aren't hydrogens in their methyl groups, for example, or any other alkyl group, they're going to be a lot larger than the hydrogen and prevent the nucleophile from entering. So because of that, this is what we call a steric effect, where sterics just refers to atomic size or substituent size. So because of that, it's harder for this nucleophile to approach if these hydrogens are methyl groups or any other alkyl halide or alkyl substituent or like a ring or anything like that, that would prevent the nucleophile from entering. And at the same time, if the nucleophile is really large, like T-butoxide or something, this type of thing is not going to happen because, again, now the nucleophile is too large. It can't get in to create this type of, intermediate, the transition state, not intermediate, that's misspeak. It can't create this transition state, which then ultimately means that you won't get to a product. The Sn2 product anyway. T-butoxide does other chemistry that's also useful, but it's elimination stuff, and I'll save that for next time. All right. Questions on Sn2, because now we'll talk about Sn1. Okay. So Sn1 chemistry is stepwise, which is the direct opposite of concerted. It's also unimolecular, meaning that only one molecule is involved in the rate. Okay, so it's stepwise. That's the first thing we'll start with. And stepwise means that bonds break and form at different times. So let's just say independently. There's no dependent relationship. It doesn't occur simultaneously. So let's look at a specific general example. So, well, it's going to be somewhat specific just because of the nature of Sn1. So let's say we have this plus methanol. Then you'd get this as a product. And if you're thinking about this like in Sn2, you're going to say, well, we have a nucleophilic oxygen. It's going to attack here and it's going to cleave this. And then we're going to get to that with a hydrogen here that we can force to leave with some weak base that we have in our solution. But this is not how this works at all. Two main reasons. So before I confuse anybody, let's say that this does not occur. It doesn't occur because the alcohol without the negative charge is a really weak nucleophile. So this is a weak nucleophile. So it doesn't favor doing this like it's drawn. Secondly, this is a tertiary alkyl halide. So those methyl groups would block this from entering like I've drawn here. So the combination of the fact that this is a weak nucleophile and this is a tertiary electrophile, it's not possible. Sn2 is not possible. So what happens is Sn1, where the first step of the mechanism, we still get the same product. It's just mechanistically different. So the first step is a spontaneous cleavage of this carbon-chlorine bond, which when I learned this made no sense because bonds don't just break because it's convenient for them to break. And you're absolutely right. There's no driving force for this step, which is why this is the rate determining step. Everything else occurs after this cleavage because now you have a carbocation that doesn't have an octet. So everything else that occurs is just going to happen very quickly since this is a very unstable. And now it's important to mention this is in fact an intermediate and not a transition state because this is directly observable. We can see it in spectroscopic data, and we can also see it in the prediction of certain reaction products. So just to summarize this point here, this doesn't happen often. So you're not just going to have a T-butyl chloride and then just have this cleave, but it will happen sometimes. And remember, Avogadro's number is 10 to the 23. So even if it happens sometimes, that's enough to drive this to actually continue and proceed. So remember, Avogadro's number is 10 to the 23. So even if this happens 1 in a billion molecules, which is 1 in 10 to the 9, that's still significant because you have 10 to the 14 more molecules left over. So if you have 1 mole of this, you're going to get plenty of this product, which can then proceed with the reaction. So hopefully I give you enough justification that this spontaneous bond cleavage isn't just way out in left field, even though it still kind of looks like it. It happens enough that you can drive this type of reaction. So once you get here, now your weak nucleophile is good enough of a nucleophile since this is a real positive charge. It has a formal charge of +1. So the oxygen can easily come in and attack that carbon. And then you get a second intermediate, which is this one here with a positive charge on the oxygen. This is intermediate 2. And now then you can have some base. So let's say the Cl- that left in the first step can come in and take this. And then you get your final product, which is the ether without the protonation. So this means there's 2 intermediates. There's a transition state here between the reactant and the first intermediate. There's a transition state here between this intermediate and this intermediate. And then there's a transition state here to the final product. So this is why I chose to show Sn1 second, because it's it's a lot more complicated because there's all these detectable intermediates and stuff. So questions on this? I'm going to relate this now to the thermodynamics with the energy diagram, and then talk about solvent effects, and that will be pretty much it at that point. It'll probably be 11:10. Okay, so that's that. So let's look at an energy diagram. So this is Sn1 energy. Here's the energy of the reactants. So I'll try to do this a little bit better than I did last time. So we have a T-butyl chloride and methanol, but methanol is just a solvent. So this I'll just put in parentheses to indicate solvent. So because it's not directly involved in the rate, which is why I was hesitating there, because I don't want to confuse anyone. Only the T-butyl chloride is involved in the rate. Okay, so anyway, then you get a very high transition or activation energy to get the first transition state, which is the case in which the carbon-chlorine bond is cleaving, like I've shown with the dotted line. Then this will fall to a stabilized intermediate, which is the carbocation. Okay, then there will be some other input of energy to get to where the methanol reacts. So this will create, let's draw it like this transition state. Well, that's not the best, but hopefully that's clear. Then that creates a new intermediate, which is this one. And then, oh, that positive charge got messed up. Okay, then this is the new intermediate. So TS1, intermediate 1, intermediate 2. This is TS2. And then there's a new hill, which falls down to the products finally. So the other intermediate, so let's draw this. Let's just say TS3 since I'm absolutely out of space. And this is the products, and I'll draw those elsewhere. So transition state 3 is the one where you cleave this bond. And then the products, which is probably off screen. Yeah, so I'll show this in a second, is the T-butyl group plus the HCl, but you don't need to really include that, but it is a byproduct. So I'll go back up here and leave this for a second and let anybody copy it who wants to, and then come back down to the other transition state in the product. So what we learn from this is that the rate, the kinetics, okay, can see it now, is the rate constant by times just the concentration of the alkyl halide. Because once the alkyl halide cleaves, the solvent is just around. I mean, the solvent is going to be a significantly higher concentration than the reactants because it's dissolved everything. So you need to have, at least 30 equivalents of it or something like that. So that concentration is going to be essentially infinite in relation to the alkyl halide. So the alkyl halide is the only thing that's limiting this entire process. So now from this, since we're forming a carbocation, we know that the more substituted a carbocation, the more stable it is. So that's why this is going to prefer tertiary by far, and it can also do some secondary alkyl halide reactions because of the stabilization of the carbocation. And there's also going to be benzylic and allylic positions that are included in this type of reaction because they're stabilized as well by their own effects, whether it be resonance or induction. All right. Questions on any of that? So what results from this in terms of stereochemistry? So we talked about how Sn2, you get the inversion of stereochemistry. Well, in Sn1, you're dealing with a carbocation intermediate, which, as we've learned from the alkene chapter, this is planar, which means that a nucleophile can attack from either side. Can attack from above the plane or below the plane. So what that means is this isn't a chiral molecule, but just for example, it means you would get this. If these groups were different, these would be different enantiomers, but in this case it's not, but still the idea applies. So essentially this is a racemic mixture. And a racemic mixture is a 50-50 mix of enantiomers. So if these are enantiomers, you'll get a racemic mixture, 50% this, 50% this, because of the nature of the intermediate, which is the carbocation. So I think we talked about everything. So rate determining step, solvent binds, 2 intermediates to 3 transition states, prefers secondary, tertiary, the rate, and configuration. Yep. So the last thing to talk about is solvent effects for both of these types of major types of substitutions. So any questions? Otherwise, I'll get into solvents. Okay. Not seeing any questions. So solvents. Both of these prefer polar solvents, first of all. So Sn1 and Sn2. Sn1 prefer polar solvents. And you can think about this it's relatively easy to understand why. Because let's say for Sn1, you have this type of thing, right, with this electrophile. So if you have a solvent that's polar, let's say acetone, you're going to then further this dipole by a new interaction with another molecule, which in essence is sucking more of the electrons away from this carbon, making this more reactive, a more reactive site. So that's why polar solvents work for Sn2. And for Sn1, it's a similar idea now. You're going to want to stabilize this intermediate. So you'll want some electronegative group. So we can stick to, well, let's make it an alcohol. So you have this type of interaction, which ultimately leads to the bond in the Sn1 case. But this explains why you want polar. But now there's this idea of protic and aprotic, which you may have not heard before. I didn't hear it before I got to OChem 1. And all it means is protic solvents can have hydrogen bonds and aprotic solvents cannot have hydrogen bonds. But this implies that hydrogen bonding is well understood, and hydrogen bonding is very specific. So I'll define what I mean here. So aprotic, no hydrogen bonds, protic, hydrogen bonds. So a hydrogen bond, as we define it in this case, is that you need an oxygen or nitrogen or fluorine that's bound to a hydrogen that interacts with another oxygen, nitrogen, or fluorine that is also bound to another hydrogen. Anything else is not considered a hydrogen bond. It's not considered a protic solvent. So for instance, let's say you have acetone and water. This is kind of a pseudo hydrogen bond because this is stronger than a dipole, but we wouldn't call this a hydrogen bond in the sense of protic solvents because this isn't there's no hydrogen off of this oxygen here. Okay, so hopefully this explains the point that now, like, if water was by itself, that's a protic solvent, certainly, because there's two hydrogens off of this oxygen now, and there's a oxygen off of this hydrogen, right? So it meets the very specific criteria that is here. So questions on that? Hopefully that makes that clear. So it's not like you're not just looking for any hydrogen on any part of the solvent, because that's not a hydrogen bond. It's very specific. The hydrogen has to be bound to an extremely electronegative group, which we define as just oxygen, nitrogen, or fluorine that are electronegative enough to get this hydrogen bonding effect. All right. No questions. So a few examples of protic solvents are like acetone or esters or substituted amides. Those are all protic solvents. There's no hydrogen on any of these electronegative atoms. And then protic solvents are like water, any alcohol, even things like, well, no, I shouldn't include that. I was going to say carboxylic acids. They are protic solvents, but they're acids, so they'll do other stuff. But alcohols is the most common. You may even see some amines, I guess, possible. Yeah, this is by far the most common too that you'll see. There's also DMSO. I should include that. That's extremely common. This is DMSO, dimethyl sulfoxide. It's kind of like a carbonyl, but it has a sulfur instead of a carbon at the center. So it's similar to acetone if you just replace the sulfur where the carbon is. So any questions on that? We have 4 minutes. So I will, I'll give you a list of 5 reaction in their conditions, and I'll ask you to determine if it's Sn1 or Sn2, and then we'll go through it. Okay, not seeing any questions, so let's jump right into it. Okay, let's go back. All right, I'll give you, we only have 2 minutes, so hopefully you got to copy these down. I'll just go through them now so I don't keep anybody too long. So what you're looking for, doesn't matter where you start. I always like to go from electrophile to nucleophile to solvent. That's just it made the most sense in my head to do it like that, but any order is fine, but you have to make at least 3 key observations about the electrophile, the nucleophile, and the solvent. So here, this is a tertiary electrophile. So right away, can't be Sn2. So since so far we haven't talked about elimination, you can basically say that this has to be Sn1. The nucleophile is good though. This is a strong nucleophile, and this is a protic solvent. So this one's a little bit tricky since I just went ahead and threw in this. If you were going to do this, you probably would just have the methanol solvent, but this is fine. This is going to be primarily Sn1 in the stuff that we've talked about so far. There would be some products of E2, but we'll get to that later. So and then here we have a secondary alkyl halide. So this could be anything, Sn1, Sn2. This is a great nucleophile. This is an aprotic solvent. So this is definitely Sn2. This is a primary electrophile, so it can't be Sn1. This is a good nucleophile. We didn't talk about phosphorus or nitrogen, but increasing atomic size is a good makes it a better nucleophile. So that's what we see here. I felt like this was a fair question to ask since it's primary electrophile, so it couldn't be anything else. It has to be Sn2. There's no solvent here in this case because this is a liquid, so that's also indicative that it's Sn2 since there has to be solvents in Sn1. So this is a primary electrophile, so it can't be Sn1, so this is Sn2. So, oops, I'm drawing the product. That's not the question. Sn2 primary at this position. This is an aprotic solvent. This is a great nucleophile. So here, this one more than likely is going to be no reaction, or at least mild reaction. And the reason is this is a big nucleophile. This is a primary electrophile. So this could happen, but it's going to be very, very weak because this bulky group here is going to prevent it from entering. So this answer, this wouldn't really be a fair question on multiple choice, I don't think, because this is ambiguous by design. It's definitely not Sn1 because this is a primary electrophile. It's weakly going to undergo Sn2. The best answer would be E2, but again, we'll talk about that next time. But my point was this is probably not going to undergo Sn2 in any significant amount because of the size of the nucleophile. I just wanted to reinforce the steric idea of Sn2 type reactions. All right, so that is all I have planned for today. So feel free to let me know if you have any questions. Yep, thank you. You too. Have a good weekend. I'll stick around for any questions, but otherwise I'll see you all next week.